Welcome, everyone. It's my honor to introduce Dr. Estel Cardellach. She is a distinguished researcher in the field of GNSS remote sensing. Her study focused on the scientific GNSS applications, including extracting geophysical information of GNSS reflected signals, radio occultation, and geodetic techniques. Since 2005, Dr. Cardellach started working with the Institute of Space Science and playing essential roles in various spaceborne missions. Currently, she is the PI of the radio occultation and the heavy precipitation experiment for the PASS satellite. So it's very nice we have her to present about the GNSS polarimetric radio occultation technique, status, and the payload for the future missions. Let's give a warm welcome to Dr. Cardellach.
Thank you. Good afternoon. First, I'll try to share. Well, let's start then. Thank you very much for this invitation. I feel very honored. I also would like to take this chance to express my deepest sympathies for the loss and the terrible situation after the earthquake you suffered last week. Let's just start with the seminar, which will be about polarimetric radio occultation. This is a new technique that I will briefly explain. Despite I'm the author of this presentation, it's important to highlight that it also contains materials prepared from other people, other scientists in UCAR, in the National Central University here in Taiwan, and also Spire Global. The seminar will be split in three main topics. The first topic will be an introduction to this technique, the polarimetric radio occultation technique. Then a central part that will explain the proof of concept experiment that is going on at aboard the PATH satellite. It's called raw path experiment. I'll explain the hypothesis and how this hypothesis has been confirmed, and then all the things that we've been able to see with this experiment and technique. And finally, the studies that we are doing at the moment to see how to use this data for operational weather prediction. And finally, I will conclude this seminar giving a bit of perspective what could be done, what is being done for future GNSS polarimetric radio occultation missions. I guess that many of you are familiar with radio occultations, given that Taiwan is contributing to two of the most successful radio occultation missions, the Formosat and Cosmic 1 and 2 missions. This is a type of technique that is based on the signals transmitted by the navigation satellites, like GPS satellites. I hope you can see my mouse. If you cannot see my mouse, please let me know. So then I can explain better to focus your sight into what I want you to look at. So yeah, the navigation satellites, they transmit signals. These signals cover the entire Earth. And when dedicated receivers are allocated in low Earth orbiters, this sketch is not scales that would be much lower in altitude, but it's cleaner if we present it this way. So yeah, I was saying we have the navigation satellites transmitting signals, illuminating the Earth, and we can install dedicated receivers in low Earth orbiters. And when these low Earth orbiters, these satellites, start to get occulted behind the Earth, what happened is that the properties of the atmosphere, the vertical structure of the atmosphere, induces the bending of these rays, these transmission links. And this bending carries information about this vertical structure of the atmosphere. For this reason, the bending angle is a very useful observable for weather prediction modeling, and you can also obtain from it refractivity, vertical profiles of refractivity of the atmosphere around the tangent point. And from there, you can also derive temperature, pressure, and water vapor. And these, especially the bending angle and refractivity information is being proved to be very successful, a very successful way to inform and to improve the weather forecast through assimilation of these data sets in numerical weather prediction models. Very large impact has been demonstrated. We also can remind that this can be globally distributed. That will depend also on the orbits selected for the receivers. It works over land, but also over the oceans. It works under all weather conditions, even under very intense systems, precipitation. And it also provides very fine vertical resolution. To me here, the important point is for you now to be aware of is that the navigation signals are transmitted at circular polarization, right-hand circular polarization. And for this reason, all the traditional radio occultation missions like Formosat, COSMIC, METOP, and many others, they also use circular antennas to receive these signals. So what I'm going to propose today is this change. The only thing I'm proposing to change is the antennas, the receiving antennas, and instead of using circular polarized antennas, use a set of two linear H and V, orthogonal H and V linear polarization antennas. And why? Well, the hypothesis is that when around the tangent point, which is this point very close to the closest to the surface, and where the propagation follows a direction parallel to the surface, tangential, in that area, if there is any precipitation, the hypothesis of this experiment and technique is that then there will be different delays for the H component and the V component, and that can be used to measure the precipitation and its intensity and get vertical profiles of an observable that relates to the precipitation. This is a new measurement concept, and it combines both the traditional radio occultation type of technique and these polarimetric properties that can be obtained after the forward scattering of big rain droplets and also other hydrometeors. As I said, this is the hypothesis of this experiment. And if successful, it represents the only sensor that can get both the vertical profiles of thermodynamic parameters, variables in the atmosphere, plus the vertical profiles of hydrometeors. There is no other sensor at the moment that can provide both types of information synchronously collocated at the same point. And to understand this, how this polarimetric information relates to the rain, we have to remind that the rain droplets, especially when they are big, those that are present in intense precipitation, are not like spheres, but they are flattened. And that's because of the dragging of the air. The heavier the rain, the more big droplets will be present. So the more elements that are not spherically symmetric, and that's important for the polarization measurements. So as I mentioned, the precipitation happens at the tangent point or around the tangent point, the area where the link between the GPS or GNSS and the receiver satellite goes tangential parallel to the surface, or we can also call it the local horizontal. An important aspect is that these navigation satellites are at L-band. That means that they penetrate all the weather systems. So whatever is going on between this navigation and the receiver, the navigation satellite and the receiver, this radio link will be able to cross and reach the receiver. Sorry. Another important aspect is that because it's circular polarized, 50% of the power is in the horizontal component and 50% is in the vertical component. That means also that somehow we lose part of the signals that reach each of the linear polarization channels here in the receiver. And the most important thing of this sketch here is the geometry, the fact that the link at these regions with precipitation is horizontal, local horizontal, and that maximizes the polarimetric phase shift. Why? As I said, the droplets are not spherical when they are big, and they are aligned. The major axis is the horizontal, so they are aligned with the transmission direction. We can then define at each point along the ray what is called the differential phase shift, which is the differential delay between the H and the V components per kilometer of trajectory. And what happens is that what we measure here at the LEO is not just one point on the ray, but the accumulation, the integration of all these differential phases. And the observable we get is the difference between the phase delay at the H polarization with respect to the V polarization. Back at the beginning of these studies, when the PATH satellite was not launched yet, we conducted a set of preliminary studies, some simulations based on the cosmic data where they were located, and we assessed that the magnitude of this polarimetric phase shift that we would measure if cosmic were a polarimetric mission would be of the order of 10 GPS millimeters. 10 GPS, well, of this order of magnitude, of course, they were just simulations. 10 millimeters of GPS signals can be converted through the wavelength to radians or cycles. And as you can see here, it's a very tiny differential phase shift of the order of 0.3 radians or 20% of one cycle. And that translates of the order of 30 picoseconds in units of time. So these are really, really tiny measurements, tiny delays. We also conducted an analysis of the cosmic noise to extrapolate which would be the expected noise with the PATH, the polarimetric experiment. We assessed that at different altitudes, the noise would be different. Note that I remove here 3 dBs, and that's to consider the fact that we only receive the H or the V, while cosmic receive the circular, which is the total available power. So what we saw is that at high altitudes, the noise in terms of millimeters would be very small, but at the surface level would be of the order of 1.5, more or less, millimeters. So still, if 10 millimeters is a very tiny value, what we see in this noise analysis is that in principle, we could still, the noise would be small enough to be able to measure these variations in the polarimetric phase shift due to the rain conditions. But all these were just simulations or noise analysis based on cosmic, were not actual measurements yet. So we still had many open questions. Was it technologically possible to measure these tiny polarimetric phase shifts? And would they relate to the heavy precipitation as we were predicting? Would that hinder the thermodynamic use of the radio occultation data? And finally, how all these measurements could be used in meteorology and climate studies. So to answer these questions, we launched the radio occultation and heavy precipitation experiment aboard the PASS satellite. And this is a proof of concept experiment. It's based on a modified IGOR receiver. Maybe some of you are aware of IGOR receivers. These were the receivers used in the first cosmic formosat mission. Agreements were signed with NOAA and UCAR for disseminating the near real-time information of the traditional radio occultation profiles, not the polarimetric ones, because the weather services cannot use them yet, so it made no sense. But the traditional equivalent, yeah, there is this agreement and it's already being disseminated through GTS. And also there were very close collaborations with the NASA Jet Propulsion Lab for all the scientific investigations. Here on the right, you can see an artistic view of the PASS satellite. Is very similar to TerraSAR and TandemX satellites. The main payload is a SAR, X-band SAR. So it's a big satellite. But in our case, we are only concerned about this antenna that you can see here. It's a few patch antenna, and each of the patches, the elements, can collect independently H and V. This satellite was launched in February 2018, and we could activate the experiment in May 2018. And it's been collecting data since then. If you are interested, there is a link here to our web, where we explain more things about this mission and the data and what we can do with all this data. If interested, we are not the only server delivering this type of data. This is our server at the Institute of Space Sciences in Spain. You can also get data at JPL. And in our case, the data that we provide for that relates to the traditional radio occultations has been processed by UCAR. So essentially, UCAR does the low level 1A and 1B, and also the level 2 to temperature, pressure, and water vapor, as if it were a right hand, a traditional radio occultation. And we inject this in our own polarimetric processing. And what we provide is the polarimetric phase shift as a function of the altitude. We also provide the ray trajectories, all the set of rays, which are the coordinates of the rays. So if someone is interested in doing collocations between these observations and some other satellite data or numerical weather prediction models, this is easy to do now because we provide the coordinates of each of the rays involved in these observations. And we also provide information about collocations with the GPM, radiometers and radars, the iMerge surface rain product, brightness temperatures, and also we inform when one of the path profiles is inside a tropical cyclone. let's continue. And let's check the main hypothesis of this technique, that was the sensitivity to heavy rain. Here again, just a summary of what we said before, and a reminder that the observable is the difference between the phase delay at the H polarization and the phase delay at the V polarization. Short after the satellite was launched, we started analyzing these polarimetric phase shift profiles, and we got a set of results. Here we have an example that's a 2D image longitude, latitude of a particular rain event. I think this is the iMerge solution on the surface. And what you can see here in gray and black, this is the horizontal, the projection of where the radio occultation rays across this system. But this is not in 2D. In fact, all these rays are vertically almost aligned. It's kind of curtain. So here in the center, what we see is how this curtain, this almost vertical cut, merges with the rain rate. And when we integrate these rays, this information along the ray, what we get is the polarimetric phase shift, that is as a function of the altitude, which is the phase shift difference between the H and the V components. We conducted some extensive analysis of 3-4 months of data. What we see is that the more intense the rain, the stronger the polarimetric phase shift. And we could also see that the structure, the vertical structure, would change as the clouds, as we knew from other data sources about the structure of the cloud. For instance, if we averaged the cases with cloud top heights above 30 kilometers, what we would get is this red line with some dispersion here. If we averaged or grouped all the cases with the cloud top height between 9 and 13, that would be the green line and structure, 6 to 9, that would be the orange, and below 6, then that would be the blue. So these vertical profiles of polarimetric phase shift also were consistent with the cloud structure. That was a way also to prove that we were measuring or we were sensitive to rain structures. But not only that, more recently, we also found that, well, let me go back once. As you can see here in these profiles, they present very high polarimetric phase shift at also very high altitudes. This is above the freezing layer. At these altitudes, there is no liquid rain. These are frozen hydrometeors. So we wanted to investigate this a bit further. And well, we conducted a set of collocations, first of all, with the GPM radiometers, the polarimetric bands at 166 gigahertz at V and H brightness temperatures. And we could see that indeed when our path measurements were positive, the differential polarimetric brightness temperatures observed by the radiometers aboard GPM were also giving more polarimetric strength. So that was consistent. And also we could also use a way to map our observed polarimetric phase shift with the one that would be given by GPM radiometers doing some trick, forward operator kind of trip, using the ice water content as input. And we can see then that our observations would fit very well what the ice information, the ice water content information given by the GPM radiometers, polarimetric radiometers. Furthermore, we did a set of climatologically comparisons between the path observables and CloudSat's ice water content. For that, we did not have actual collocation. So what we did is to take the CloudSat orbits. CloudSat provides like vertical curtains with the ice water content information, and we simply simulated the radio occultation ray paths, that is these shapes that you can see here. These are the rays, and let's see this example here, zoom in. So then we could integrate these values to get this integrated ice water content. So the data is from CloudSat, but in the geometry, how this path, in the geometry of path, right? So that would relate to the path type of observations, in that case as an integrated ice water content. And then we compare, because we did not have actual collocations, we compare the climatologies. For instance, here on the top right, what we see in black is the average integrated ice water content as a function of the latitude, that's latitude. While on the, that's with this scale here on the left, while on the right and with red, what we have is the same, but for the polarimetric radio occultation's differential phase shift. And we can see that the statistics fit very well with each other. In a similar way, this scatter plot also shown very good, almost one-to-one link between the polarimetric phase shift at a given region with the integrated ice water content at the same region by CloudSat. So with that, we proved that this technique is not only sensitive to heavy rain, liquid heavy rain, but also the ice water content at the freezing layers. And finally, we just conducted recently some validation exercise with NextRad. NextRad is a network of polarimetric weather radars, ground-based radars that are located across the US. And what we did is to just search for path observations that were well fitted in one of several of the radars. And then what we do is to interpolate or to give values along the radio occultation paths, ray trajectories of the NextRad information. We need a couple of transformations. One is to pass from the S-band of the radars to the L-band of the path radio occultation, polarimetric radio occultation data. And then also we need a correction for the geometry, which is slightly different. And when then we compare the path polarimetric phase shift in red here as a function of the altitude, we compare it with what would be the equivalent from NextRad. We see that in general there is a good agreement. This comparison and validation has been published very recently. It's a very recent paper. I invite you to check if you are interested. And now, how to use this data? Because as you have seen, this data contains a very long integration along the range for hundreds of kilometers. So how can we use this type of information that has very fine vertical resolution, but not too good horizontal resolution? And well, there are many scientists working on different scientific applications of this data. What I'm going to present today is only what could be the use of this data for operational weather forecast. We envisage two types of applications. One would be as a diagnosis tool to help identifying and refining the parametrization used in the numerical weather prediction models. I'll talk about that later. But then also what would be ideal is the data simulation. This is only a starting now. And in fact, last year, there was the first paper about that to present a forward operator. And that was done at ECMWF. This is not my own work. This is extracted from this paper at ECMWF and the Japan Meteorological Agency too. And what we can see here is that they compared the path in thick blue with what this forward operator could predict about the path observations based on the information that the weather model would say about different hydrometeors like ice, liquid rain, snow, convection rain, convection snow. And we can see that when they sum up all these contributions from the model, it fits reasonably well with the path data. That means that with this forward operator, they can start thinking about data simulation experiments. But now let's present how to use it for diagnosis. Precipitation is very difficult to model and to forecast in numerical weather prediction models and WP models. And there exist different ways of parametrizing all these aspects that involve rain, hydrometeors, the clouds. It's what it's called the microphysics schemes. There are many of them. And the results using one or the other are obviously different. Can this type of observations help identifying which is the suitable scheme for different scenarios? What I'm going to show is just an example. And that was a collaboration between us and also the Taiwan's National Central University, and was based on a regional numerical weather model called WRF, WRF, sorry, that was run at this Taiwan National Central University. What we'll see, well, we found examples in 3 different tropical cyclones, but what I'm going to present is just for one of them, the Bualoi in 2019. We can see here an image of the cyclone and the path, polarimetric, radio occultation rate trajectories mapped into the surface. And what we see here are the simulations of WRF in these big panels across the polarimetric radio occultation plane. And different colors relate to the different types of hydrometeors. And each of these panels is for a different microphysics scheme. And as you can see, all of them look reasonably different. Some of them look more closer to each other. And what we see is that when this is, when we generate the equivalent of the path profile, the path profile as a function of the altitude is the black one. When we generate that from the model, the final one, which is the light blue, in some of the microphysics do not look like the actual path measurements, but in some of the microphysics they do. So we could use this data to try to see which is the microphysics that better explains different type of phenomena. And finally, to conclude with this last, let's say, 10 minutes of seminar, I'm going to talk about perspectives for new polarimetric radio occultation missions. And in particular, we are interested in knowing if this technique is suitable for the new space approach. As you've seen, the PATH experiment is aboard a very large satellite. It's a SAR satellite. I think it's more than 5 meters long satellite, so very heavy. Could this technique be implemented in small nanosats and CubeSats? Well, in fact, this has been done recently, and last year, the company called Aspire Global launched 3 CubeSats with this type of technology. And not only that, but compared to PATH, these receivers expanded the capabilities, because PATH can only use GPS signals, while these receivers on board this CubeSat could also receive Galileo, GLONASS, and Beidou. And it could also collect multiple simultaneous profiles, while PATH is very limited in these terms. One of them was developed under a NISA contract called Progress, and we did the validation at our institute. What we see here in this plot is the polarimetric radio occultation data available since the launch of PATH. All this time is simply PATH. And then last year, when 3 CubeSats were launched with these expanded capabilities, boom, the total amount of data simply multiply it. And now during a period of time, there were almost 200 and 500 polarimetric daily radio occultations. That's quite new, and that permits to study many more things. First of all, let's look at the quality of these profiles. Do the fact that they are collected from CubeSats hinder or worsen the quality of the polarimetric observations? And the answer is that in general, no, the quality is similar to PATH. There is even an improvement at the bottom layers. It's better than PATH. Here in black is PATH, the PATH standard deviation when there is no rain, so the noise. And in different colors, the 3 different satellites by Aspire. In some areas, maybe it's slightly noisier, but not significantly, taking into account that this is 0.5 millimeter and the signatures are of several millimeters and tens of millimeters. So this is good, but not only that, what they found is that also for the thermodynamic profiles, the combining H and V from polarimetric RO, they get better performance than when they use directly the Aspire RO data. Yeah, so it seems that it's possible to implement very well this technology in CubeSats and in the new space paradigm. Also, the response to rain was very similar between PATH in blue and Aspire Global in orange. We can see the same type of response, so that's also good. And finally, what is very interesting is that for the very first time with these data sets, what we got are clusters of observations that happen very close in time and space, as we can see here. This with PATH was not possible, but with just these 3 satellites, we got many clusters of observations. And this type of clustered information can be very useful. And in fact, it was proposed as a mission constellation, a small constellation to NASA a few years ago. And the reason is that it has a scientific interest to better study and understand all the life cycle of these intense precipitation and convective systems. There are a couple of papers that explain which is the scientific use of this type of clustered information. And it's interesting that these papers were written before we got any cluster of data of polarimetric RO data from Aspire Global. Yeah. And well, I think with that, we reached the conclusions. Just a reminder that this is the polarimetric radio occultation technique. This is a new technique, and it's useful to measure both the thermodynamic and hydrometeor vertical profiles in the atmosphere. There is a proof of concept experiment still going on aboard the PATH Spanish satellite. It's called ROPATH experiment. And the hypothesis of the experiment was confirmed. We got sensitivity to non-spherical hydrometeors at different altitudes, so vertical profiles. And that includes not only heavy rain, which was the original hypothesis, but also other frozen particles above the freezing layer. And at the moment, there are several studies going on, some of them just for scientific applications, but some others for the operational weather forecast applications of these data sets, this technique. And one option is the data simulation, and that's just beginning this type of studies. An important milestone was achieved, which is to be able to forward to simulate the data from numerical weather prediction variables, what is called a forward operator, and that was already achieved and published last year. And we are also working towards using this data as a diagnosis tool, given that these data are sensitive to different microphysics schemes, so it could be informative for the models. Finally, what we saw is that this technique is also suitable for the new space paradigm, and it can be installed and working correctly from very small satellites, even CubeSats, as Aspire Global has demonstrated. And not only that, but even using these very small satellites, they were able to extend the capabilities of the original proof of concept experiment, and they also can get multiple GNSS constellations and simultaneous profiles, and that enables or has potential to enable new science possibilities. And with that, I'm concluding this seminar. So now I'm open to any questions.
Thank you, Dr. Cardellach, for this very nice presentation. So if anyone have questions, please feel free to turn on your mic and just ask. So I have a quick question. So you just show an figure that compare the PL and the transition out. There's some difference, major difference at the lower level below about 2 kilometers.
Are you talking about the, why I cannot go back now? Oh, here. Are you talking about the spire, this profile?
Yeah, this one. So why there's large differences at the lower troposphere?
Well, probably this is a matter of the receiver itself, the algorithms inside the receiver, the way they are tracking the signals in path at some point. It's not as efficient as the algorithms, the tracking algorithms that are implemented in the Spire receiver.
Okay.
It's just a matter of how the receiver works. The path, the modifications we did to Igor were minimal. So essentially it was like the Cosmic Formosat 3 receiver, and we had the V and H channels were not properly synchronized. So we had a set of drawbacks because it was not designed for polarimetric arrow, while Spire did design the receiver thinking about this technique. Yeah, not just reusing the existing receiver with for instance, we did not synchronize that makes things a bit more difficult. There are more residual cycle slips that are different H and V and so and so. Yeah, that's at the bottom layers. That's at the end. It's very important and worsens the measurement.
Okay, I see. So do you have similar comparison with something like Cosmic 2 with the past? Will they have such large differences, or they just become more comparable?
Oh, this I don't have it in mind. I'm sure that there are some comparisons done, but I don't remember what happens with the traditional radio occultations once you combine H and V. It's likely that it's also worse, yeah. for path.
Thank you.
Thank you.
Shuji, please go
Hi,
ahead.
so this is Shuji Yang from NCU, and thank you very much for this wonderful talk and sharing this very new technique and progress with us. So I have two questions. First is that I think this is I really like the idea that we can use the polarimetric RO and select the most suitable parameterization scheme for NWP. So I wonder, to do that, does that means that we so how long should we collect this type of the PRO profiles to construct this kind of radio occultation map that you show? So that's the first question. And the second question is that maybe I'm a little bit this is relatively new to me. So when assimilating the PRO compared to the conventional RO like bending angle profile, so for the model, is there anything particular, for example, the vertical resolution or horizontal resolution to conduct this kind of experiment? Thank you.
Thank you for these two questions. I'm going to try to answer the second one first. All right, for data simulation, I'm not sure about, I don't work with numerical weather prediction models, but I think the requirements in terms of vertical profile are fine with the technique. So the technique provides at the end of the order of a few hundred meters vertical resolution. And I believe the numerical weather prediction models work with vertical layers that are more or less at these scales. So I think for the vertical, that's sufficient, that's okay. For the horizontal, what happens is that, well, in general, I think would be better to have something with better horizontal resolution, but working with forward operators is good, because then you don't care if the data is a long track in integration. At the end, you can also simulate that with the model. So, of course, with this finer horizontal resolution, that probably would be better for this diagnosis, but I think it's still useful because of the forward operators. Yeah. What else I wanted to say about this? No, it skipped. I don't remember. I had something else to say about this, but yeah, I don't remember now. And regarding the first question, I'm not sure I understood what you mean by how many, so for how long or how many pro data we would need to generate which maps?
I'm not sure, maybe I misunderstood. There's one slide showing the different type of hydrometers, and yeah, this one. So okay. Yeah, so to construct this kind of map, I assume that we will need several PRO profile. Right. So no, yeah.
No, sorry. Maybe I did not explain it properly. This is just for one profile. All of them, it's the same profile. It's one particular profile, which is shown here in black and repeated here and here. So that's altitude, and that's the polarimetric phase shift. In black is the path profile. And to generate this profile, or the synthetic one, the one from the models, that's the output of the model. The output of the model is a 3D mesh, and that's interpolated to the rays, the location of the rays of the radio occultation, the polarimetric radio occultation. I don't know if you can see that there are some gray lines that have this kind of shape. Yeah, this would be the polarimetric radio occultation of one particular profile, just one profile. And so then the 3D fields of the model are interpolated to these locations of the rays, and then integrated along the ray. And for instance, for this ray here, if we integrate of all this blue and we locate it, we assign it to this tangent point height, then that would be this blue, you know, it's, and for here, this ray here, we would integrate all these fields along this ray, and then the integrated value we would assign to the tangent point altitude. That would be this value here, and so and so. So this is just one single polarimetric radio occultation. The actual data is only the black, and all the rest is just numerical weather model and the expected ray trajectories. I'm not sure I'm explaining this very well.
No, it's very clear. Sorry, I misunderstood this figure, but it's very clear now. Yeah, thank you.
Okay, thank you.
Is there anyone have other questions? If let's know, so let's thank again to the Dr. Cardellach for a wonderful, very nice presentation. Thank you.
Thank you for the invitation. Have a nice afternoon.
Thank you very much.
Thank you.
Okay, bye.
Thank you. Bye-bye.